Good Thursday. This is the last Algebra 2 class of this week. We are going to cover 4-7. Yeah, okay. Inverse and identity matrix. If you are listening to this recording, I hope that you have at least read through this section. And if you haven't, well, maybe do it at the same time. So it's on page 195. And it's talking about inverse and identity. What do you remember about regular, inverse, and identity? Nothing. Miss Chris says nothing.
Sorry.
What about you, Jessica? Do you remember anything about regular numbers and inverse and identity?
Oops.
Uh-oh.
Hold on, I just killed the mouse. It's okay. I think I yanked your cord on accident, Flavia. Did the phone come unplugged or no?
No.
Oh, okay.
No.
I don't really remember much about inverse either.
Okay, well, okay. What's the inverse of 2? The multiplicative inverse. Oh, Miss Chris says 1/2. How'd you get that? Right. But what happens when you multiply them? They equal 1. Yeah. So 2 times 1/2 is 1. So matrices have that same idea. When you multiply 2 matrices together and get something called the identity matrix, well, look at that, then they're inverses. Seems pretty straightforward, except it is not just a number. It's a whole block of numbers. Zeros and ones, in fact. But first we're going to learn about why they are useful. And computer geeks probably know this one. Who wants to read and how are these things useful? Okay. Yeah.
With the right internet shopping, securing the privacy of the user's personal information has become an important priority. Companies protect their computers by using code. Cryptography is a method of preparing coded messages that can only be ciphered by using the key to the message.
Right. I think that's a really great use for matrices. And you can, for instance, they have in the box, so this is how it works. First, you assign a number to each letter of the alphabet. It can be any letter. It could be A is 5,642. But are you going to remember that? No, so you probably should write it down, right? Once you assign a letter to each, or a number to each letter of the alphabet, then you convert your message into a matrix and multiply it by the coding matrix. And your coding matrix can be whatever the heck you want it to be. It could be 0, 1, 5, and 6,000. It's just a set of numbers that you have written down somewhere that when you multiply your coded message matrix by that matrix, you'll be able to get, you'll be able to figure out what it's saying. And then to decode the message, the recipient of the coded message would multiply by the opposite, or in other words, the inverse matrix of the coded. So you find the inverse of the little coding matrix that you made up from your head. So see the table right below there? 0. So a dash is 0. So I think they mean space, though, not like a dash. So if you hit a space in your code, it's a 0. If you hit an A, it's a 1, B, 2, C, 3, and so on, till you get to Z at 26. So if I was to write dog, right, that would be 4, 15, 7. Dog. Does that make sense? Yeah.
Yeah.
You know, plug and chug. That's our favorite word to say. Plug and chug. And that's one useful way. And to decode it, say my coding matrix was like 3, 4, 5, 6. You would multiply that 3 by 1. I'd have to come up with a 1 by 3. Okay? Multiply it by 7. Then you do the opposite thing to get it back again. We'll see in example 3. All right. So how do we figure out what the identity and inverse matrices are? So again, recall that in numbers, two numbers are inverses if their product is the identity 1. So 5 times 1/5, 2 times 1/2, 3/4 times 4/3. They're all inverses of one another. Similarly, for matrices, the identity matrix it's a square matrix. It's always a square matrix. That when multiplied by another matrix equals that same, just like 1 times 2 is 2. That matrix times the identity matrix is the same matrix. So if A is an n by n matrix and I is another n by n matrix, identity matrix, excuse me, then A times I equals A, and I times A equals A. So that means if you put the identity matrix first and times it by the one you were given, it should be the same as the other way around. Okay, look at the 2 by 2 identity matrix. Does everybody see it? Just above the key concepts box. We're still on page 195. Do you see it, Jessica? Where it says 2 by 2 identity matrix? Yes, no. Jessica? Hello? Uh-oh. I am. Jessica's gone. Well, we added some. How long has she been gone? I don't know. Yeah, I want to pause recording.
Okay.
Okay, so you found it, right?
Yep.
Okay, yes. 1, 0, 0, 1. Well, look below, and what does the 3 by 3 identity matrix look like?
It's 1, 0, 0, 0, 1, 0, and 0, 0, 1.
Right. So do you see a pattern?
Yes.
Yeah. All the ones are in the big old diagonal from bottom or top right, blank, blank, top left to bottom right. And all the rest are filled in with zeros. So
Yep.
what do you think a 4 by 4 would look like? A 4 by 4
There would be there'd be a 1 on the top left, and then a 1 in the second column, or the second column of the second row.
Right.
Third column of third row, and then yeah.
That's right. That's a really important thing to know. Okay. Well, look in key concepts. We're going to see why this works. They do it in symbols, of course, because, you know, math loves its little symbols. So again, when you multiply any matrix by this I, the identity matrix, you should get the matrix you started with. If you didn't, you probably messed up on your calculation somewhere. Hopefully you guys remember how to multiply. Okay. The identity matrix for multiplication, I, is a square matrix with 1 for every element on the main diagonal, from upper left to lower right. I just repeated myself. And 0 in all the other positions. For any square matrix A, capital A, the same dimensions as I, so you have to have the same dimensions, A times I equals, if they have the same dimensions, I times A equals A. Phew! So, remember how we found out the commutativity of matrices is false? This is the only time it works. This is the only time. All right, let's see what they're talking about. If matrix A equals 2 by 2 matrix A, B, C, D, then I equals 1, 0, 0, 1. So what happens when we multiply this? A times 1 is
A.
A. B times 0 is 0. So A plus 0. Oh, so far so good. Okay, now first row, second column. A times 0? 0. B times 1. B. We just found A and B. Not too bad, huh? And then, of course, you do the second row. You get C, the second row, first column. In the second row, second row, second column, you get D. Because those 1s and all the 0s cancel out every other additional term, don't they? Well, hooray! All right, I'm not going to read the little blurb at the bottom of the page because it's a lie. So turn the page, and Braille, go find the page break.
I got it.
Let's look at example 1. We're going to verify. Let's verify if these two matrices are inverses. So, do you see matrices X and Y in little a?
Yeah.
2, 2, negative 1, 4 for X. 1 half, 1 half, negative 1, 1 fourth for Y. What do you notice about the first element in each of these matrices? Yeah, they're inverses. What about the second one? So what do you think? This seems, yeah, they're all inverses. So this seems like it would be that it would work. Like, oh, that looks pretty good to me. I mean, they're inverses. Let's find out. So in order to check, what do we multiply this thing by? We gotta multiply them together and see. All right. They kind of do it for us. Check if X and Y equal I, right? Kind of like we do 1 half times 2 to check if they're inverses. So put X first. So how do we start to multiply somebody? First row, first column. Yeah, 2 times 1 half is plus 2 times negative 1. So what's 1 plus negative 2?
Negative 1.
That's right. So is that the first element of our identity matrix? No.
Yeah.
So, right, it has to be a positive 1, doesn't it? Because it was 1, 0, 0, 1. So does this work? No.
No.
If you find one error, you don't have to go on like the book does. I'm happy that you found a 1 and said, oh, it can't be the identity matrix because there's a negative 1 in there.
So if you give us something like that on the test, we can just stop right there. We don't have to.
Yeah, as long as you say why you're stopping. Don't just write negative 1. I'll be like, what? What is negative 1? I might not get why you wrote. Does that make sense? Say, oh, negative 1 is not part of the identity matrix. So it can't be, the X and Y cannot be inverses. Because I am not one to make you work harder than you have to. But I mean, if you really wanted to, 2 times 1 half is 1. 2 times 1 fourth is 1 half. Obviously 1 half plus, or 1 plus 1 half is 1 1/2. That's not 0. And we could keep going, but we already figured out it was wrong. Okay. Let's look at little b. What about P and Q? What does P say, Jessica?
It says 3, 4, and 1, 2.
All right. And Q, we have 1, negative 2, negative 1 half, 3 half. This looks weird, doesn't it? 3 and 4 and on the first row and 1 and negative 2 on another first row? How can this make sense? Okay, well, let's try it. First row, first column, somebody.
3 times 1 is 1.
Right. 3 times 1 is 1? You sure?
Oh, no. Sorry,
Not
3.
Jessica. 3 times 1 is 3. Okay. Plus?
I don't know what you asked.
Right. What's 4 times negative 1 half? Negative 2. So what's 3 plus negative 2?
1.
1. Okay. So far, so good, right? We got a 1. First row, second column.
Okay. 3 times.
Huh? First row, second column.
Oh, yeah.
3 times -2.
Okay, what's that?
-6.
Okay, and 4 times?
Yeah.
All right, what's 4 times 3 over 2?
3 over 2. 6.
All right, so what's -6 plus 6? 0. We're still going strong, right? We want these identity matrix elements. Okay, Josiah, first row, or second row, first column. Your turn, because you're all quiet. Second row, first column. Wow.
Yeah.
No. 1 times 1.
Second row, first. Oh.
Yeah.
Gotcha.
Yep.
1.
Plus. Negative. -2 times 2 times -1/2.
Oh, I see. Okay.
Yeah, second row, first column.
Negative.
Okay, so what's 1 plus -1?
0.
Yay! Okay, last element. So now we have 1, 0, and 0. So Miss Chris, is it your turn?
I'm not following. I'm sorry. I was looking up something.
Ah, okay, I guess it's my turn. Okay, first or second row, second column to get our fourth element. Okay, 1 times -2 is -2 plus 2 times 3 halves. That's 6 over 2, which is the same as 2. So -2 plus 2, or excuse me, I gotta restart. Okay, -2 plus 3. -2 plus 3 is 1. Oh, we did it. So guess what? So far, P and Q, it works. But remember, we got to go the other way, at least in this example, but for whatever reason in the homework we don't have to. Okay, so now we got to do the same thing for Q and P. First row. And so, again, when you switch them, remember ordered, if you already did it the one way, you got to do it the other way. So 1, -2, -1/2, 3 halves. We're looking at where it says now P, Q. You just switch the order, of course, and do the same old thing again. First row, first column. 1 times 3 is plus 2 times, or -2 times 1. So it's 3 plus -2? 1. Okay, 1 times 4 is, -2 times 2 is 4 plus -4. Okay, so far so good. Now we're on the second row, first column. -1/2 times 3. Oh, excuse me. No, I'm right. Yeah. -3 halves, and then 3 halves times 1. Okay, so -3 halves plus 3 halves. 0. Last one. Okay. -1/2 times 4. -2 plus 3 halves times 2.
Oh, 3.
3. So what's -2 plus 3? Does it work?
Yes.
Hooray! Now that was just a quick reminder also of what multiplying is. So again, it's first row, first column, first row, second column. Then you move down to the second row, first column, second row, second column. Well, let's figure out how we can find the inverse without having to check like that, because we won't always have both matrices to check. So to find the inverse, there's a cute little formula.
So it has to work both ways. Is that correct?
Well, okay, here's the deal. The book says on the bottom of the previous page that it's supposed to. But I find it funny because commutativity does not work in matrices. We learned that a couple of sections ago. You remember?
Well, that's why I was
And
wondering
so,
if it does for inverse.
that's why I skipped that little blurb and said, it worked for this particular matrix, but it won't work for every matrix. So, in the homework, just check the one way you're given. Okay? The book lied. I think the book lied, but I might have to do some independent research to find out.
I'm thinking maybe it works for all inverses, though.
No, because you found out that QP and PQ in the one homework didn't work one way.
I'm thinking maybe the book was wrong and it should have been no instead of yes, and maybe it works for all inverse.
Well, when we get there, I will try them, okay? Let's get through on how to find it first. All right. Everybody see key concept? It's in the middle of the page, 290, kind of near the bottom, actually. Or 196. I don't know why I said 290. Okay. So we have a cute little formula about how to find the inverse of this matrix A, B, C, D. Does everybody see that part? I want you to read the little formula with your hands and eyeballs. Is A inverse? That's what A to the negative 1 means. A inverse equals 1 over AD minus BC times this new matrix, D negative B negative C A. Does anybody remember what AD minus BC looks like? Should look pretty familiar. You might remember it from Monday, Jessica.
Those equations that we were doing the other day, I forgot what it was though.
Determinant. So
There we go.
to find the inverse, you do 1 over the determinant of your matrix times this new fancy matrix. So all they did was they swapped A and D. So they put D where A was and A where D was, and they did the opposite of B and C. Does that make sense? So D moved, A moved, and then B and C just turned opposite signs. That's it. And it also says where the determinant of the matrix can't be 0. What happens if the determinant of the matrix is 0? Nope. That's right, it's undefined. 1 over 0 doesn't make any sense. So all you have to do is say, well, if I get 0, then you can say, oh, there is no inverse. Does that make sense, Jessica?
Yep.
You can't have 0 in the denominator. Okay, so again, it's 1 over the determinant scaled to the matrix where A and D are swapped, and you have negative B and negative C. So D, negative B, negative C, A. Let's try it. Top of the next page. 297. Find the inverse. Are you dropping a phone again?
Yeah, actually, I think I did. Sorry.
Well,
Thanks.
I'll wait if you hang up again. Do you see example?
Okay, well, I'm still here for now. So.
Okay. Example 2 is right after the page break in Braille.
Found it.
Okay. Find the inverse of each matrix, quote, if possible, quote, or if it exists. All right, matrix R. So when you do these, obviously, if the determinant doesn't exist, then you should try finding the determinant first, because then you'll know if you can bother doing it, right? Okay, what's the determinant of this matrix, and how do we find it, somebody? Right, so how do we find the determinant? Okay, go ahead. Multiply those diagonals.
Alright.
Uh-huh. So what's negative 24 minus negative 24? 0. So does this matrix have an inverse? Nope. I bet you B will. So slide your fingers and eyeballs down to part B. For P. P is the new matrix. P as in people. Yep, that's the one. What's the determinant, Jessica?
1.
It is 1. Did you cheat?
No.
Oh.
I just did it on the calculator.
Oh. Smart. 3 times 2 is 6, minus 1 times 5 is 5, so 6 minus 5 is 1. Well, that's great, right? We have 1 over 1 times the matrix. Well, what's 1 times anything? Anything. So, hey, we don't have to scale it. Okay. So how do we remember, and you guys have notes, what matrix to multiply by? Right. You can look in your book or in your note. What I remember is you change the 3 and the 2 around. The 2 starts and the 3 is in the bottom right. Yep, A and D swap. So the first element should be a 2.
And you negify your...
Yes, and then you negify the other diagonal. I like that. You negify, so you switch the first diagonal, and you negify the second diagonal. So it would be 2, -1, -5, 3. And that is your inverse. Oi! Yep. So, and the book checks it for you. And see, Miss Chris, how when they check, they only do it one way.
Okay, where am I looking?
The check at the very bottom of the example.
Okay, just, I gotta see what I'm looking at.
They found the matrix 2, -1, -5, 3. So everybody see where they check? They check by multiplying
And
them.
they're multiplying it by the normal one.
First.
Okay, so how do you know at that point which should come first in the multiplication, whether they should start with the one they got or if they should start with the original?
Well, they started with the inverse, see?
I see that.
Yeah. So I don't actually have an answer to that question.
Oh, okay.
I want to do my independent research. But in theory, you should be able to do either one. In theory. Okay? And we can check right now if we did it the other way, but I'll do that while you guys are working.
Okay, so multiplied together, they should give you the...
What should it get, you guys, when you're multiplying
What
two
is that
matrices that might be
called?
inverses?
What is
The
that?
identity.
That's right, the identity matrix 1, 0, 0, 1.
All right.
Now, for example 3, I just want to talk through it. Because we read about it at the beginning of the chapter, about how to decode messages. I'm not going to make you do one on the test or anything like that, but I do want to talk about it because it's kind of cool. So they want to use the table from the beginning, where 0 was a space, 1 was A, 2 was B, and so on, to decode a message. So example 3 says, use the table at the beginning of the lesson to assign numbers to each letter in the alphabet. And then, so they want you to decode the phrase go dash tonight. And so, to do that, we have to figure out what G-O space T-O-N-I-G-H-T are in our number matrix. And then they give us the coded message matrix, A equal, and again, like I said, it can be anything you want. 2, 1, 4, 3 in this case. Ha, I just switched, it's 1, 2, 3, 4, right? If you were reading it counterclockwise. Anyway, so what they had to do was convert the message into numbers. So G is 7, O is 15, space is 0, T is 20, so on. So all the way to T again is another 20. And so you have to write this message in matrix form. And then, of course, multiply it by the coded matrix. Okay. So they have the coded matrix written as a 2 by 5. That's because, see how it's 715, that's go, 0, 20 is space T, and so on. Can we multiply a 2 by 2, or 2 by 5 and a, come on, brain. Can we multiply a 5 by 2 and a 2 by 2? Can we do that? Yeah, because it's row by column. So 715 times 2, 4. I'm not going to have you do all that. But that's why the book wrote it out for all of us. What will the answer be when you multiply a 5 by 2 and a 2 by 2? That's right, it'll be a 5 by 2, your outer numbers. Are you still there, Jessica?
Yep.
Okay, just checking, you're quiet. I didn't. That's a good thing. And so they did all this work for you. And on the next page, because they wrote it out and added for you, on the top of the next page, you finally get your new matrix. That's the coded message you'd send. 74, 52, 80, 60, so on, all the way down to 96, 68. That's kind of awesome. I want to make a code now. So the coded message is now 74, 52, 80, 60, 57, 46, 30, 96, and 68. So you just write it pair by pair. Whew, coded message. Okay, but how do we get it back, right? We just figured out how to make one, so how do we figure out how to get it back? Well, all you need to do is multiply this coded matrix, the one that's a coded message, by the inverse of the little 2 by 2 matrix they said was the coding message, two, 1, 2, 3, 4 counterclockwise things. So we have to find the determinant of that. It was 2, 1, 4, 3. Right. Because that's the decoding matrix. That's how we can figure out, in order to decode the coded message, we have to multiply it by the inverse of our code, like our code, our 2 by 2 code, which is the 2, 1, 4, 3. So to find the determinant, well, you guys should know how to do that by now. So it will be 1/2 times, and remember the whole swappy thing, 3, -1, -4, 2. So swap the first diagonal, negify the second diagonal. I like that word, Miss Chris's, negify. And apparently, when you look at that, look at the very bottom of the example, did they get it? Heck yeah, they got it. They got 7, 15, 0, 20, and so on. And so you can rewrite it out in a line, and that's go tonight. Now, if it were me, I would totally be more savvy. Like, I wouldn't pick 1 for A, you know? Like, that's too easy. I'd pick all the vowels having some crazy prime number, and then all the composites being, or all the consonants would be perfect squares. Just it's more fun. But again, it's a simplified version of the code. So anyway, don't worry, I'm not going to kill you guys with these. It's, on page 199, you're just going to do 5 through 8. 4 through 8. 4 through 8. Page 199, problems 4 through 8. It's about checking whether these are inverses and finding inverses. 4, 5, 6, 7, and 8. That's right. All right, Stormy, we hope you're getting better.